Bismillahirrahmanirrahim. Today's video is about Laplace transform from signals and systems. And here we'll be primarily discussing example 9.1 and 9.2. And this is on the request of a student. So let's recall that we have read about the phasor domain or the frequency domain. In that, what we do, we take the time domain signal or and then convert it into frequency domain and then solve it, which becomes easier in frequency domain. And then we go back or invert it to time domain. Exactly same or similar phenomena occurs in the Laplace transform. Time domain, then we transform into Laplace domain. And from Laplace, we go to inverse transform to time domain. The only difference here is that in case of a Laplace, we use complex signal or we deal with the complex signal, whereas in case of a phasor domain, we just transform the signal into frequency domain. So we can say that a signal xt, when transformed in Laplace domain, it will be written as capital X, and in bracket we write S, and this symbol shows that it has gone through the Laplace transform. The definition of Laplace transform is that whatever is the signal, we multiply that by e raised to the power minus st, and then we integrate it from negative infinity to positive infinity. And also, actually, S or the symbol for Laplace consists of two terms. One is called the sigma, and the other is called omega. So sigma plus j omega is representing S or S domain. And we use this type of a graph for plotting. The horizontal axis is representing sigma, or we can also say it is representing real part of S. Now this was S, so this is the real part of S. And the other thing, this axis, vertical axis, is representing the imaginary part of S or j omega. So j omega or imaginary part in the vertical axis, and horizontal axis is real part of S or sigma. So in this definition, if you replace S by sigma plus j omega, we'll get an equation like this, just S replaced by S plus sigma plus j omega. So both these equations are used. And just to give you an idea, if we open this one, then we'll get e raised to the power minus sigma t and e raised to the power minus j omega t. Now j omega t basically is a sinusoidal signal, you can see cos and sine, and its net value or the magnitude is equal to 1. So what is determining here is this term, e raised to the power minus sigma t, and whatever is the value of the signal itself. So that is why it is very important that we understand or find out sigma. And this, you can have an idea from here that if this is the oscillating signal, and if it is multiplied by this term, which is called actually the damping factor. So the damping factor is gradually reducing it if the damping is convergent, or it can take it to infinity if it is non-convergent or infinite signal. Now let's come to the example. Signal xt is e raised to the power minus at ut, and we know from the definition of Laplace transform, this xs can be written as infinity to infinity integral of xt est dt. And now if for xt we replace the signal itself, which is ET, the EAT UT, e raised to the power minus ST. Now we know what is UT. UT is a unit step function which has a value of 1 and which starts from 0, not from minus infinity. So first of all, because of UT, we'll change this limit from minus infinity to 0. And UT's value is 1, so no need of writing 1. So this is what is left. And this can be written as 0 to infinity e raised to the power minus s plus a or a plus s from here dt. So this we'll call equation number 1 from here. Now, in finding the answer or specifying the Laplace transform of a signal, two things are important. One is called the algebraic expression, and the other is called the range of value of S for which this expression is valid. This is also called ROC, region of convergence. So we'll see that. Okay, so this was the signal. And now if we integrate, we'll get this term and we'll put the limit here. Now there are two possibilities that this value of S plus A, it could be positive or it could be negative, that is less than 0, greater than 0, less than 0. You can also say why not equal to 0. Okay. So S plus 1 equal to 0 we don't consider because at this point, that is when S is at minus 1, the Laplace transform will always be infinite. So we know this, so there is no point writing it. But in these two scenarios, it could be finite here or it could be finite here. So we'll see that with these two examples. Okay, so this is now we're rewriting and we are saying that S plus A is positive. And to make it easy to look, we just put a positive sign here in the bracket. So what will happen now? Negative sign multiplied by positive is negative. So we can write it as this value e raised to the power negative t. And the limit remains here. Putting in the values of the limit now, e raised to the power minus infinity and e raised to the power 0. I'm sure you know the value of e raised to the power minus infinity. I'll just repeat it. E raised to the power minus infinity can be written as 1 over e raised to the power infinity. And e raised to the power infinity is infinity. So 1 divided by infinity is equal to 0. Therefore, this one will become 0. And e raised to the power 0 is 1. So our equation of this becomes 0. This is 1. Multiplying negative, negative becomes positive. So we get 1 over S plus A. And this is a finite value. We will say that the Laplace transform is finite or it converges. Let's see what happens in the second scenario. And now this is S plus A is less than 0. That means it is negative. Now put a negative sign. Now negative, negative, positive. So we can write it this equal to e raised to the power positive t and the limit. And now putting the limit, this is e infinity minus e0. And anything e raised to the power infinity will become infinity. So this whole thing will become infinite. And therefore, we'll say that the Laplace transform does not converge, becoming infinite. So one thing clear. Now, so we were here, this we are now neglecting because this is making it infinite. The condition for convergence, so from here we can say that the condition for convergence is that S plus A has to be greater than 0. Or we can say S will be greater than minus A. And this moves up to the right hand side. Or we can also say from here that we'll take this one is greater than -1. From here we replace this. But as we mentioned here that the j omega's value is not important to us. Sigma is important, or sigma is the real value of S. So we can say that the real S has to be greater than -1, sorry, -a. Now, what is -a? -a is any value on the real axis line. So let's say we mark it here. This is -a. So the first thing we do is we draw a parallel line. This line is parallel line at -a. And now we'll see where the signal lies. You see, we have said that the real value of S has to be greater than -a. So -a is this point. So our signal will be on this side, greater than -a. And so this is our region of convergence, that our signal will converge in this region. And this is called ROC also. The final answer, we can write it like this, that this was the input signal. Laplace transform of this is 1 over S plus A. So this is the magnitude. And the ROC condition we have to write that real part of S is greater than -a. So this is how we write the complete answer. So 9.1 is done. Now let's see 9.2. The only difference is this minus sign here, and we have u raised to the power -t. This was the 9.1. This is 9.2. So see the difference. This minus sign is addition, and instead of ut, it is u minus t. So we'll use the same formula. Just plug in the value of x e raised to the power st, and we just move it right hand side. This is here. Now u minus t is what? We know u minus t is starting from 0 and going towards the negative side. Its value is 1. Or we can say that we start from negative infinity up to 0. So we can replace or remove ut by changing this limit. So the limit now will become minus infinity to 0, EAT, EST, and ut we have replaced. From here, we can write e raised to the power minus s plus at dt. And we integrate, so we get this result, and this is our limit. And same way that we did in the previous example, we take two possibilities. This is greater than 0, or it can be less than 0. First, let's solve this. S plus a is positive, so positive, negative t, so e raised to the power negative t, and this is the limit. Putting the limit, e raised to the power -0 minus e raised to the power infinity, t and t, minus will become plus, e raised to the power infinity. And now, since there is a e raised to the power infinity, the whole thing will become infinite. So we can say that the Laplace transform does not converge in this case. Now keep in mind, in the previous case, for example 9.1, it was converging at this point. Now let's see the second part now. So here again, we'll now saying that s plus a is less than 0 means negative. Put a negative sign, so negative, positive. It will be e raised to the power positive t, and the limits. Plugging in the limits, e raised to the power 0, minus e raised to the power minus infinity. We just learned in the previous example that this will become 0. This is 0, this is 1. So our final answer is 1 over s plus a, and this has a finite value. So we can say that the Laplace transform is finite, or it converges at this condition. So we were up to this point. For the convergence, or the condition for convergence is that s plus a is negative or less than 0. From here we can say that s is less than negative, or we can put sigma plus j omega to be less than a, or we can say the real part of s is less than a minus a. Then we will plot, this is our minus a point, but where we draw the ROC line, the real s has to be less than minus 1. So this is minus 1. Less than means it will be on the left hand side. This is the region of convergence. So the final answer will write that this Laplace transform is 1 over s plus a, and the region of convergence is RES less than minus a. I hope you have been able to follow this. Please let me know through your comments. Thank you.